Frances Arnold was born in 1956 in Pittsburgh, United States. She got her PhD in 1985 at the University of California at Berkeley. She is now active as a professor at California Institute of Technology in Pasadena, also in California. Frances Arnold pioneered directed evolution of enzymes. She used her engineering skills to make this method a most versatile tool for developing biocatalysts for new environments and for new tasks. She has made a strong effort to make this planet a better place. The enzyme she develops can be used to speed up chemical reactions in a sustainable way, making less waste in a cleaner process. We call them fantastic biocatalysts. Now, Frances Arnold, I invite you to the stage to deliver your talk.
Thank you. Thank you. I'd like to thank the Royal Swedish Academy of Sciences, the Nobel Prize Committee in Chemistry, my family, many of whom are here, my friends, even more of whom are here, and especially I'd like to thank my former and current students, and I know there's a group of you here, because it's really their contributions that I'll be talking about today. I'm an engineer. I have been in awe and mesmerized by the chemistry of the biological world for some time, because it's this incredible diversity of transformations that gives rise to all the beauty and functionality that we see in the natural world. The complexity of the products that nature makes. And when you think about how she can assemble these products with ease and elegance and remarkable efficiency from simple, renewable, abundant starting materials, to me that's a real inspiration for chemistry of the future. Now, who does this chemistry? It's the enzymes, these remarkable, marvelous molecular machines that catalyze all the reactions in the living world, almost all the reactions in the living world, and that are DNA encoded. Now, I'm also in awe and inspired by the enzymes, but also by the process that nature uses to create them. And in fact, that nature uses to create everything in the living world, evolution. It's a remarkable diversity-generating machine. It's a simple algorithm of mutation and natural selection that gives you a recipe for adaptation, for optimization, for innovation, and has created all the life that we see around us, starting from a universal common ancestor, a simple life form, more than 3 billion years ago. Now, I wanted to build new enzymes, and protein engineers, like I was in the 1980s, we struggled mightily with a simple problem, and that is we didn't understand, and we still don't today, enough about how a DNA sequence encodes function in order to be able to reliably design a new enzyme. That's why I turned to nature's process. So here's the problem. Even today, we can read DNA, we can write DNA. You can just email a sequence off to your favorite supplier, and you'll get it back in the mail. We can edit DNA, CRISPR-Cas. We have all these tools, but what we do not know how to do, and this is the problem that I took on 30 years ago, is how do you compose it? It's like a Beethoven symphony, the code of life. It's intricate. It's beautiful. But we don't know how to write like that. But nature does. You have this process. So we can think of all the proteins that exist today, in fact, all the way back to the universal common ancestor, as this set of proteins that are relevant to biology. And biologists, this is what you study, this little green place, because that is but an infinitesimal fraction of the possible proteins. We can think of this universe of all possible proteins as a playground for the future. This is where I want to explore. And I want to explore here because I think the solutions to many of humanity's biggest problems lie in this space. Now, this is a challenge, of course, because this space is vast. It's bigger than the universe, the number of particles in the universe, by many, many orders of magnitude. This remarkable short story by Jorge Luis Borges, The Library of Babel, describes, for all practical purposes, an infinite library of all possible books. And the librarians there are in despair. How could I, if I want to search this universe of sequences, which is like all possible proteins, but I know that most of those possible books encode nothing at all. They're just gibberish. These random combinations of letters don't compete with pumping oil out of the ground, for example. How could I search this library and find something meaningful? So this is a tough problem, because if you look at this space, it's so big. And we've heard some very big numbers in these experiments. Gazillions. Well, I cannot search for gazillions. I don't have 10 to the gazillion graduate students, or even 10 to the 9th graduate students. And if we look at, for a large protein, now we've gone from peptides to antibodies, which can be quite large, but we go to something like an enzyme, that space of possibilities is enormous. If you make a single mutation to a typical protein, you have thousands of ways to do that. You start making 2 and you have millions of ways. You make 3 and it just grows exponentially. We cannot search this space just without thinking a little bit about the process. Now, John Maynard Smith helped me address this problem in a marvelous paper that he wrote, published in 1970, my favorite 1.5-page paper. And he said, consider proteins in an ordered space where every sequence is surrounded by its neighbors that differ by one mutation. And he argued that if evolution is to occur, and he believes it does, and I think most of us here believe that evolution happens, functional proteins have to be distributed in this space so that any functional protein, something you can scrape off your shoe, is surrounded by at least a few other functional proteins. Forming a network may be sparse in this space where most sequences are gibberish, forming a network where evolution can walk along. And that's exactly what proteins have done for the last 3.5 billion years. They've accumulated mutations, one at a time primarily, to create what the proteins are today. Now, of course, I want to make better proteins. I want to make enzymes that will solve human problems. So let me add one more dimension to this, and that is the fitness, the performance, how an enzyme performs a new job. And that's defined by me in this set of experiments. And we can think of this now as an optimization problem on a fitness landscape. Now, in the 1980s, we knew very, very little about the structure of this landscape. It could be rugged. And if it's very rugged, then most mutations are deleterious and send you into a crevasse of non-function. And evolution is very hard in that case. On the other hand, if it's smooth, and John Maynard Smith helped argue that it has to be smooth in its dimensions for us to be here to talk about it, then you can use simple optimization processes. Now, science, like all human endeavors, is an evolutionary process, right? It builds on what is there, and we recombine different pieces from different places. And a lot of interesting things were happening in the 1980s. You've heard about some of those. And in the early 1990s. For example, Manfred Eigen was talking about experimental molecular evolution. And Jerry Joyce was evolving RNA in the laboratory, directing the evolution of RNA. Jeremy Knowles showed us that beneficial mutations in proteins could be accumulated. Stuart Kaufman was talking about the theoretical fitness landscape searches. And then for me, Dan Dennett, a philosopher, gave me wonderful words and framework for the ideas that I was trying to work on. And all of these came together in a simple process. Now, the difference between my experiments and those that you've heard about is that I don't have an affinity selection that lets me search through 1 million or 10 million or 1 billion different molecules. We have to measure them one by one, because you get what you screen for in this business, and if you're looking at an enzyme, you need to measure what that enzyme does. Maybe we can test a few thousand things or a few tens of thousands of things. Most of those mutations are deleterious. So this meant that we had to be very careful about how we were going to carry out this optimization, making just a few mutations at a time, maybe one at a time randomly in the molecule, screen carefully to measure the small effects that you would expect to get from a single mutation. And then if you wanted something that was very different from what you started with, and believe me, choosing that starting point is important because you don't get a racehorse from a donkey. So you choose that, that's a very rational thing. If you want something quite different from what you start with, then you have to iterate. You have to accumulate those mutations over multiple generations. And this gave us an experimental process that has proven its value. So if you start with your donkey, and most enzymes are pretty good. Nature's done a good job optimizing them for their job. But if you start asking it to do a new job, for me, they're less enthusiastic, let's say. And that fitness drops dramatically. But on this smooth fitness landscape, a simple optimization of accumulating mutations over multiple generations can re-optimize it for the new job. That work from the 1980s that we started this culminated in this first paper published in 1993, where Kevin Chen showed that we could adapt an enzyme to what was considered a highly non-natural environment. In fact, it was so non-natural that many biochemists told me, oh, you can't do that. It won't work. An enzyme will never work in dimethylformamide. In fact, they don't like it at all. But what we showed is that with a few mutations and doing this process, you could convince it to work just as well in 50 or 60% DMF as it did in its natural environment. In 1995, I met Pim Stemmer, shortly after his DNA shuffling paper was published. We met at a workshop at the Santa Fe Institute, and I was taken with his vision. He introduced this idea of sexual recombination. So this is another search strategy for evolution. Seems to work pretty well. There's a lot of diversity you get by recombining your DNA with somebody else's. And Pim talked about this as a molecular breeding process, and I often use that when I present my work. Now, sadly, Pim passed away in 2013. But he started a company that pushed a lot of this technology, mine and his, out into the world. And as a result of their work at Maxigen and many, many other laboratories, this directed evolution process has created enzymes that you will find in your laundry detergents, that are used to manufacture pharmaceuticals, that are used in all sorts of different industries today. I'm very proud of those applications, none of which I'm responsible for. But that's the nice thing, if you provide a basic framework that's simple, and this is what engineers like to do, make it as simple as possible, then the whole world will be able to use it. But we learned some very interesting things about enzymes in the process of doing that. Of course, they will adapt rapidly. We didn't know this at the time. We didn't know how many iterations, how many mutations it would take to get a new function out of an enzyme, or to make it function in a non-natural environment, or take a new substrate. And those came rapidly. We also learned that we're a long ways away from being able to design them, because I knew this process would be useful back in the 90s because we knew it was fast, but also that the solutions that you got were so surprising. Mutations happened all over the protein, 20, 30 angstroms away from the active site, where no one could explain them, much less predict them. So here we have this marvelous optimization mechanism. And that's what I've told you about. You take a biological enzyme and you can optimize it and change it for different functions. So now I'm going to fast forward into today so that I can end with the future. I'm interested today not in the optimization so much, although that's very important, but actually how does evolution create novelty? How could you create enzymes to catalyze reactions you cannot even find in the biological world, or at least we haven't found them yet? You cannot go to a database and find an enzyme that catalyzes your favorite reaction. How could we import reactions even invented by human beings, 100 years of creative chemistry? How could we import that into the efficiency of the biological world and genetically encode whole new chemistry? And at first I thought that would be a really hard problem, because we all know enzymes are so beautifully designed. They position their functional groups to catalyze a reaction and stabilize a transition state. And how do you create a whole new active site? It's a very conservative process, what I just described to you, making one mutation at a time. But that's the wrong way to think about it, because nature's making new enzymes all the time, usually to break down your billion-dollar antibiotic, but usually in response to pressures that humans have placed on this planet. So here's a great example. A potent herbicide that we've been dumping into the environment, onto our fields for more than 60 years, was first thought to be non-biodegradable. Then all of a sudden, some enzyme figured out how to dechlorinate atrazine, giving a rich nitrogen source to the organism that invented it, and it spread all over the world. This is evolution in real time. Evolution in real time every time you use antibacterial soap. We're causing and pushing evolution, but it's happening quickly. So how does this happen? How do you get evolution in real time? Well, it happens that enzymes already have those capabilities. They're like graduate students. You're selected for working long hours at low pay, and you can do that, but maybe you could also play the piano or do dishes if you had to. If chemistry was no longer a viable field for work, you could go and switch into something else. Well, enzymes are just like that. Any enzyme that exists today has promiscuous capabilities that evolution uses as a fuel for further invention. And if you can find those promiscuous capabilities, I'm the trainer of molecules, I have to see those, then you can use this simple turn the crank, presto results process of directed evolution. So let me give you an example. I love the cytochrome Cs because here's a family of enzymes that nature has diversified to carry out all sorts of interesting chemical reactions, and many of you are familiar with these. Nature uses one or a set of closely related, highly reactive intermediates to do this. And presumably through this process of mutation and selection has diversified this family. Now we argued in looking at this that, wow, this looks a little bit like human invented chemistry. If you could convince a cytochrome P450 to create a reactive intermediate that has a carbon, these are reactive carbines in the active site, make an iron carbanoid. Maybe you could convince it to transfer that and do human chemistry, like turn double bonds into cyclopropanes, or insert that carbene into an XH bond. This is not known in the biological world. was invented by human beings, but if we provided the right synthetic environment, think atrazine, right, a new niche for the enzyme, and this tool of directed evolution, perhaps we could create enzymes for these new human things. So it becomes a question, can a heme protein create these new reactive intermediates? And there was some evidence that that would be possible. But then the hard part, would it take that, and instead of using it to chew itself up, would it transfer that to a second substrate? So now you've got to have two substrates coming together in an enzyme that's never seen these before. And if you can see that little bit of activity, does it evolve? 5 years ago, we asked these questions, and I'll just give you one example of much more recent work that we did. In fact, these do carbene transfer. We've created a whole bunch of carbene transferases, and one of the ones that I love to talk about is one that does chemistry that even humans have a really hard time doing, making highly strained carbocycles like bicyclobutanes, which is a transformation not known in the biological world. And even in the chemical world, the world of human chemistry, it's very difficult to do, and it requires precious metals. So iron, earth-abundant iron, was never known to do this. But Kai-Chen showed that he could make cyclopropenes. We have more than 50 kcals per mole of ring strain in these structures. And that by providing a carbene precursor to this, the enzyme would form the reactive carbene, transfer it to that, and furthermore, it evolves. So Kai-Chen discovered an enzyme sitting in our refrigerator. I have a tremendous collection of interesting heme proteins, and he just said, can you do this as a promiscuous activity? And then he showed he could evolve it over multiple generations to become a reasonably efficient catalyst. But even more wondrous is that he could further train the enzyme to do it twice. So if it hangs on to this reactive cyclopropene in the active site, he can now add a second carbene. So you blow off nitrogen with this, that drives the formation of the carbene. You can now add a second, and make bicyclobutanes, pure diastereomers. You only make one of the 4 possible diastereomers because the enzyme creates the environment where this remarkable chemistry can take place. Furthermore, the enzymes can make lots of bicyclobutanes. Now, as far as I know, nobody wants bicyclobutanes. If anybody wants them, please let me know. But these are interesting molecules that really have evaded human chemistry. But here an enzyme just learned how to do that in a few generations. And they happen inside living cells. So you do this chemistry just by providing the substrates to bacteria in a culture, and they'll spew out enough of these so that we can assign the absolute stereochemistry. Let me give you another example. Consider bonds that are unknown in biology. Here we have silicon, an element that is so abundant on our Earth's crust and has never been found bonded to carbon in the biological world. There are no carbon-silicon bonds in biology. Some people have wondered why that's the case. I'm not going to answer that question, but now they are found in biology because if you go to my refrigerator, you can find proteins, for example, from this hot, salty pool in Iceland, from an organism that grew there. And that protein, if you just search through these, that protein will take a carbene precursor and this silane, dimethylphenylsilane, and insert the carbene into that silicon-hydrogen bond and make new organosilicon compounds. Just a wild-type protein. No one ever asked if nature could do it. Of course, these are not naturally abundant compounds, but nature's capable. Nature has the inherent capability to do organosilicon chemistry. 40 turnovers, that's as good as the best human-made catalyst. Just a natural protein, 97% enantioselectivity. Oh, and by the way, I just point out, this is a cytochrome C, and it is so stable you can boil it. Even a chemist can use it. It's so stable, it just looks like a powder, and it works beautifully for this chemistry. The native function of this cytochrome C is electron transfer. And in fact, if you know anything about cytochrome C, you'll be puzzling, whoa, how does this happen? Because the active site where this chemistry takes place, if you look at the crystal structure of this protein, you see that the active site is all filled up with protein. The iron is fully saturated. All the ligands from the porphyrin ring and the axial ligands above and below just fill up the active site. So if you roll your little ball over the computer, you find a big fat 0 for active site volume. But nature doesn't care about your calculations because this protein is perfectly happy to do this chemistry. And our pictures, our simple pictures of proteins don't do justice of what's actually happened. Not only does it do this chemistry, but this protein also evolves. So that if you make mutations near the active site over 3 generations, you can evolve the low promiscuous activity of the wild protein into something that now becomes dozens of times better than the best human catalyst. Just turn the crank, give them a little bit of sugar, and the proteins will evolve. And it works inside of bacterial cells. Why is that important? The bacterial cells will make your catalyst and make millions of versions of your catalyst for the price of sugar. So if it's DNA encoded, and these are all just, you put the gene into the bacteria, if it's DNA encoded, you can just grow all the catalysts that you want and mutate it 1,000,000 times for the price of sugar. And here I show you an example where, for example, you could choose between putting that carbene on silicon or on nitrogen, and if you've evolved the catalyst, it chooses only the silicon. So you get chemoselectivity, enantioselectivity, all done by the bacteria. Now, when this story was published, it went all over the world because everybody said we're making silicon-based life. That wasn't the case. I don't have time to go into some of the funny things that came about it, but apparently nobody actually read the paper. They only read the title of the paper. So it went around the world and mutated the story as it went around the world. And it gave my group a lot of fun, laughter, reading the Twitterverse interpretations of how we were creating silicon-based life. But it works in life, and you could conceivably build silicon into living systems, now that you have genetically encoded chemistry. You can also learn how the protein learned how to do this. You could get the structure of the protein, and in this case, we see that the structure has changed dramatically. We have a loop over this active iron that has completely flipped out into solvent. There were 3 mutations that were made in this protein. It's caused this loop to flip out and opens up a volume, a pocket here that has sufficient volume now to accommodate a large number of different substrates and do this chemistry extremely efficiently. Dozens of times better than the best catalyst that was ever published by a human being. If you can do it with silicon, you can do it with other atoms as well. And so, for example, recently, a year later, we just published, excuse me, the incorporation of carbenes into boron H bonds. And yes, there are no boron-carbon bonds found in the biological world. And here's a bond that's very much favored by chemists, a very versatile system, organoborons. But you can take an enzyme or a protein like cytochrome C and just turn the crank. So you're starting to get a little bit of the pattern here. You discover a little bit of activity, you have this wonderful optimization process, and we can find by starting with the 0 generation wild-type protein and evolving over 3 generations, you now have something that when you use it under optimal conditions is 400 times better than the best human catalyst for the same reaction. Does it with earth-abundant iron. And you can, of course, also change the selectivity, tuning the catalyst for the chemistry that you're interested in. I'll just point out that in the biological world, one criticism we face if we want to do biocatalysis is that, oh, you can't do what I can do. I have great chemists at Caltech who can do and create materials that biological world can't do. But I hope that's going to change, because I've just shown you, even though biology is limited to the bonds that it can make. So carbon, for example, is often found bonded to nitrogen or oxygen or sulfur, a little bit to the halogens, a few other things, lots of hydrogen, of course, but there's vast portions of the periodic table that we have never found a biological system to do. And I just showed you, in the course of 2 years, we've added 2 whole elements to biology's repertoire. So you can now build carbon boron and carbon silicon scaffolds in living systems, and of course then do further chemistry on that in metabolic pathways. So I would like to leave you with this idea for the future, because I'm really excited about now, but even more so about the future of this science, that we have this incredibly powerful design algorithm, right? It works at all scales, from molecules to ecosystems. And it not only optimizes, but it can innovate, and it can do it in real time. And in the chemistry world, what that does is open this opportunity basically to take down the barrier between the natural chemistry and human-invented chemistry, and just import all those human inventions into the biological world. You just sit there, and I sit there and read chemistry papers. My students read old Jack's journals, and they say, wow, I bet I could import this reaction in. And I haven't shown you many of the other ones that they've been successful in doing. But this is an exciting thing, I think, for the young people, because by marrying these different fields, it's like you're in a gold mine of possibilities that you can now genetically encode and make much easier some of your favorite chemistry. And I'd also like to leave you with this idea that the biological world is wonderfully diverse. There is a bazillion proteins out there just waiting to solve your problem. And nature knew this, right? The internet of things. No, it's the internet of living things that's been crowdsourcing, problem solving for more than 3 billion years. And if we learn how to use this to our benefit, we can move into a much more sustainable future and make our fuels and chemicals using biological systems. So I'd like to leave you with this idea that we have a universe to explore. We have a spaceship for exploring that universe. It's called evolution. And I want to thank the very large number of people who've worked with me over the years at Caltech. A big fraction of them are shown in this picture. They came for one of my big birthdays a couple of years ago. And once again, I thank them, and I thank you for your attention.
Francis Arnold, George Smith, and Gregory Winter, thank you all for wonderful talks. And I now welcome all 3 of you up on the stage to take all the applauses. Okay.